God. You're mute.
Hello and welcome everyone. My name is Claire Brown. I am a senior consultant at Turner & Townsend. We are joined today by two fabulous speakers. So we have Alistair Cameron from ECD Architects and Amit Sharma from RYBKA. I hope I got that right. We will be recording the session, but not the Q&A at the end. This is a North Eastern Yorkshire Net Zero Hub event, which is delivered by myself and colleagues at Turner & Townsend. As I said, we will have a presentation followed by a nice amount of time for Q&A. The slide deck will be made available after the event in a follow-up email for everyone, so you can digest some more of the content at your own leisure. The recording also will be uploaded to the Net Zero Hub website shortly after that as well. If we do have questions, please do kind of use the chat and we will kind of pick those up at the end of the session. Please do try and keep your microphone on mute while we have the presenters providing us with their presentation. Massive welcome to everyone and thank you for joining us on this Thursday lunchtime. We'll hand over to Alistair and Amit. Thank you very much.
Thanks very much, Claire. Afternoon, it's afternoon, isn't it, everyone? I'm Alistair Cameron from ECD Architects, and as Claire says, we're going to talk about decarbonising leisure centres. I'll let you guys be the judge of whether this is a masterclass or not at the end of it. I don't know if signing up to that, I might have had second thoughts, but anyway, so we're going to talk in particular about the Waterfront Leisure Centre, which is in Inverclyde in Scotland. So just to give you a little bit of background, we've done some sort of decarbonisation studies for Inverclyde Council previously on their education estate, looking at retrofitting them, and they came back to us with a couple of very bespoke building typologies that were real problems for them, and that was one of them was the Waterfront Leisure Centre and also the municipal buildings there. So they wanted us to have a look at those buildings with particular focus now they might decarbonise them, and they also wanted us to have a look at the potential for an energy centre too, which Amit will talk to you a little bit about. But for those that don't know Inverclyde Council, it's a pretty small council area in Scotland. It's just to the west of Glasgow, right on the Firth of Clyde. And as I say, the Waterfront Leisure Centre was the one that we were looking at. So that's a photograph of it. Not a bad building from that aspect, but definitely on the two sides. We've got this lovely facade on the other side here, and anybody who knows anything about retrofit will immediately identify where all the big issues are with this one in terms of thermal bridges, and I don't know if it's supposed to be a whale or an upturned boat or something, but anyway, interesting design. We'll leave it at that, I think. So we'll look at I'm an architect, obviously, so I'm interested in the fabric considerations. So if we have a quick look at that first. So what we tend to do when we are asked to look at this kind of thing for clients, quite often passive house and EnerFit is the big buzzword when it comes to these, and we've been doing these for quite a number of years now, and we've come to recognise that pretty much nobody can afford to do passive house or EnerFit. We do all these lovely presentations and reports, and we get to the last slide on the presentation and watch people's jaws drop when we give them budgets. So we've learned to kind of come back from that a little bit and really looking at how to retrofit buildings to allow the energy or the heat demand to be met by a decarbonised source. So that's really where we're coming from. But in any case, passive house is still a good methodology and a good place to start. So what we tend to do is we look at each of the buildings and we carry out what we call a passive house scoping study. So it's really just looking at the kind of 5 fundamentals of passive house, like sort of thermal bridge and orientation, you know, glazing, heat, overheating, that kind of thing, and just see how well that building's performing. So this is just an example of the kind of thing we look at. This is looking at the building's orientation, and ideally it should be within 30 degrees of due south, the principal facade. This one's sitting slightly more than that, but as you'll see from the previous images, this building had a real issue in terms of a lot of glazing on both sides, both south and north. In fact, the client seemed to think that it was actually a building that had been designed for a different site and had actually just been put here. So if I just jump back to the images here, that's the north facade of the building there. Lots of nice views out over the Firth of Clyde, but in terms of heat loss, the majority of that facade is north facing, and all it's doing is losing heat essentially out of the building. And then on the south facade, this is all just sort of semi-translucent glazing. So a real issue in these areas with overheating in the building. So we've got one side of the building that's overheating, one side of the building that's losing a lot of heat. And then actually when you get into the building, that's further exacerbated. We've got this kind of warm space area at the top. These are the kind of offices and you know, ancillary spaces, but the building also has a number of hot spaces. We've got a swimming pool in the building, which obviously generates a lot of heat, and there's a proper swimming pool with lanes, but there's also a kind of play area too. In the centre there where the warm space is, that's a gymnasium there. And then to the left-hand side, the cold space, they'd actually retrofitted an ice rink into the building as well. So again, in terms of solar gain and heat loss in the facades, we've got issues there, or an imbalance rather. But then when you look at the internal heat zones as well, there's a complete imbalance there where we're generating a lot of heat in one part of the building, we're trying to lose it in another part of the building. So it's really quite complex scenario that we're looking at in that building. And that can be seen in the existing heat analysis. So these bar charts are normally what we get out of the PHPP, the Passive House Planning Package. So we tend to use that as architects. Amit will talk a little bit about the modelling software he uses. But as architects, we tend to use this so we can understand a bit about where the heat's going in the different areas and how much energy is being generated. And you can see that the heat demand in the cold spaces and the warm spaces is sitting about 170, roughly about 150 across the two of them, which is pretty typical, we would say, for existing buildings of this type. But when you look at the hot spaces, which is the pool, it's nearly 1,200 kilowatt hours per square metre per annum. So it's massive. It's 10 times the amount of heat demand in that area as opposed to the other two. So some real key issues there in the building, which frankly, as architects, we will struggle to remedy when it comes to that. That really demands a sort of M&E focused solution. But we'll stick to the fabric at the moment. So in terms of the fabric upgrades, we've got a number of things which we could look at doing. So from the photographs that showed, obviously they have this kind of ribbed feature on the front of the building. The structure's coming right through the building fabric there, and it's just creating a number of really large thermal bridges coming through the building fabric there. And that's actually leading to corrosion of the steelwork on the inside of the building as well, just because of the temperature delta between the two of them and the moisture as well. So there are solutions to potentially overclad or wrap some of these elements here to stop that thermal bridge, and that would be fairly easy to do. When they retrofitted the ice rink into the building as well, they didn't actually install any insulation into the walls which separate the ancillary spaces from the ice rink. So you've essentially got a constant sort of 2-degree temperature within the building that's just putting coolth into the rest of the building. So we can tackle that by installing insulation into the internal walls. And in terms of the differential between the warm space, the cold space, and the hot space, which I showed in the diagram previously, again, there's no insulation internally in these walls. So we could look at installing insulation between these walls here to try and control that temperature transfer a little bit better. But in terms of the actual fabric of the building, the outside fabric of the building, there's only really one option there, and that's to reclad the building. So the front of the building at the moment, like I say, the one which is facing south, the only way to really deal with that is to reclad it and cut down the amount of glazing. And again, for the opposite reason, but to the north, again, we want to cut down the amount of glazing there. So those, oh, I'm sorry, I should say as well, this diagram up in the top left, top right-hand corner there, that's actually an external flume as well. So, I mean, that's a lovely big cold bridge right through the building as well. So obviously you'd want to encapsulate that. But these are massive moves for a building of that type. You know, you're essentially talking about recladding the entire building, and the cost of that is phenomenal. I think we worked it out to be around about £6.5 million just to do that level of work, and that wasn't even including potential structural changes as well to that. So there wasn't a structural engineer involved in the study. So real implications for that building there with limited benefits actually. Because this is the sort of heat demand chart of the building, the kind of waterfall chart that shows the individual measures that could take place. But you can see there for the overall, the combined heat demand of the building is very high when you take into account the swimming pool. And really for £6.5 million to get to the section on the right-hand side there, where the final step would be improving those thermal bridges, you are reducing the heat demand, but it's never going to really pay itself back just because of the energy use in the building itself. So like I say, this was really what the conclusion we came to, was that there was limited benefit for this particular building typology of doing fabric upgrades unless there was already a demand for replacing some of the glazing that was life expired, for example, in which case you would, you know, upgrade the spec on these elements. But in terms of just decarbonising the building, which was what we were asked to do, it was really driven by an M&E strategy. So I'll hand over to Amit now, who will talk you through that.
Thank you, Alistair. So I'm Amit Sharma from RIBCA, and we work with Alistair and ECD Architects on the M&E strategies associated with the feasibility study for the Waterfront Leisure Centre. And as Alistair mentioned, the building itself, you know, has a very high energy requirement with the swimming pool and the ice rink, and it's got a very high kind of energy load intensity. And with any fabric improvement, although it was contributing to a reduction in energy use, the actual capital cost associated was extremely high. So for that reason, we decided to take a slightly unconventional approach where it wasn't necessarily fabric first in all instances, and there was opportunities to maybe do or propose some of the mechanical and electrical actions first, and the fabric would then later follow. Now, as part of the study, we looked at the Waterfront Leisure Centre and its relationship with some surrounding buildings that were either owned and operated by Inverclyde Council or were publicly funded buildings or publicly run buildings, to see if there was any opportunity for a district energy or district heating approach. So the Waterfront Leisure Centre, which is number 5 on the image, it's adjacent to an ocean terminal building, which also houses a museum and a restaurant. There's also a building called Custom House, which is an A-listed building, which is currently used as offices. And then there's a newer building which was constructed in the last 10 years called the Beacon Art Centre, which includes a theatre and arts and kind of community use halls. Away from the Clyde, there is a police station. It's a large 1970s police station, which has 60 cells, so it's quite a big building, and you know, it has quite a significant energy demand associated with it. And then across the road, we've got 2 council buildings which are currently used as their kind of headquarters for kind of office application. So we've got the GMB, which is the municipal buildings, and the James Watt building. And that's predominantly office accommodation, but it is kind of listed buildings, historic buildings, and quite large in terms of footprint. So it was quite important for us to gain an understanding on how the Waterfront Leisure Centre sat in relation to its neighbours. When we looked at the various buildings in and around the waterfront leisure centre, it became apparent that the leisure centre itself had a significant peak heating demand in comparison to its neighbours. So the table that's on the screen, it shows that the leisure centre itself, when you accumulate all the heating loads to do with space heating, pool heating, domestic hot water, the demands alone are, in excess of 3,000 kilowatts peak load. And if you compare that to the GMB, the municipal buildings, which is probably a larger footprint in terms of GIFA, and it's also a listed building, a lot older, its peak load was only 880 kilowatts. So you're comparing over 3,000 kilowatts to 880 kilowatts. And I think that puts it into perspective how much energy the waterfront leisure centre is consuming in comparison to some of its neighbours. And when you look at the annual demand, that further kind of illustrates the energy intensity of the building. So annual demand of the leisure centre, and it's not including any cooling associated with the ice rink, is 6.2 million kilowatt hours. And again, just comparing that with the police station, which is 1.4 million kilowatt hours, and the Greenock municipal buildings, which is 1.9 million kilowatt hours, it just shows you that the leisure centre is a massive energy consuming building. It has high carbon emissions and it's very expensive for the council to operate. This graph here kind of further puts it into perspective, where we're looking at the monthly heating demands of the building in comparison to the neighbours. So it might be difficult to read on screen, but the yellow section is the leisure centre, and the red is the GMB building. Sorry, I flipped. Sorry, yeah, thank you. So you can see that the monthly profile of the leisure centre is, significant. And even when you accumulate the other buildings, the other 6-7 buildings, you're probably looking at the leisure centre being still a greater energy demand in comparison to its large neighbours, which we found quite interesting. So if there was an opportunity to capitalise on this and to look at a district heating approach by creating some kind of central energy centre, and that energy centre would essentially serve these buildings and provide low carbon heating to these buildings, and by default reduce the carbon footprint of the buildings, we felt there was opportunities to do that through a centralised approach. So as part of the study, we did look at what sources of heat could we take advantage of to provide a district heating solution. So, the building itself, the waterfront, is blessed because it's adjacent to a river, it's adjacent to the Clyde. So there was opportunities there to utilise the water by having some water sourced heat pump solution. And there's also good ground conditions around the waterfront leisure centre. There's large car parks, there's green area. So again, we could look at ground source heat pumps, either open loop or closed loop. And the other option would be to use the air and have air source heat pumps. So that's taking advantage of the environmental opportunities in and around the building itself. But also interesting was that the main sewage pipe for Inverclyde was on the adjacent A road, adjacent to the leisure centre, and that sewage pipe created an opportunity to use energy from waste. And we had conversations with Scottish Water with regards to how much energy we could essentially take from that waste pipe and transfer that energy to heat energy to serve the building. Not just the leisure centre, but also the adjacent buildings. So they were the kind of the main sources of energy that we felt we could capitalise on. When we reviewed the viability of each option, we generally came to the conclusion that using the water from the Clyde was a viable option, and we could capitalise on that and create a low zero carbon heat source. And then second would be the wastewater from the sewage pipe on the A road, which was it's a pipe, it's over 1 metre diameter, and it's got a high flow rate, and there was opportunities there to capitalise on that and create heat from waste. So with all options, there's various types of district heating that we felt would be applicable and viable for the development, and we looked at various options, and some of these are tabled in this on this slide. So the first option, which would be the air source heat pump using air and electricity as an energy source, and that would essentially provide kind of high-grade heat to each of the buildings, and then you transfer that heat into the building via a plate heat exchanger. Now, because we're not taking a fabric-first approach, the vast majority of the buildings that have been mentioned on this presentation slide are operating at high flow and return temperatures. So generally speaking, the waterfront leisure centre, the GMB, the police station, the ocean terminal, they're all operating at heating circuits in and around 80 degrees flow. So there wasn't an option immediately to reduce that flow rate without making significant changes to the building's heating systems by upgrading pipes, pumps and radiators and heat emitters, which wasn't something we wanted to do because that would further increase the capital cost of the investment. So for us to make the system work at day one, we would have to operate the heat pumps at a high flow temperature. So the third generation, which we classify as high flow temperature heating, you'd essentially be running the heat pumps at an 85 degree flow to complement the existing heating network. So option 1, air source heat pump. Option 2, water to water heat pump, either using the River Clyde or wastewater from the sewage pipe. And then option 3, which is the kind of the low cost solution, which is essentially just using electric boilers and not taking advantage of any coefficient of performance. Option 4 was an interesting one. This is using what we classify as 5th generation district heating, and that's essentially creating an ambient loop. So that's low grade energy serving each building, and then we upgrade that energy local to the building. So essentially, with 5th generation district heating, we're essentially potentially just taking water from the Clyde at 10 degrees, and that water is fairly stable throughout the year, and that energy at 10 degrees is then upgraded locally via heat pumps, water to water heat pumps at each building, and that gives the buildings the opportunity to provide a heating medium that suits the building and its performance requirements. So if there was, for example, fabric improvements made to the Waterfront Leisure Centre or fabric improvements made to the GMB building, and that building no longer needed heating at 80 degrees, we could locally adjust that at the local heat pump at the building and essentially take advantage of the efficiencies associated with that reduction in temperature. Now, looking at the 4 options that we presented to the client, we did an analysis based on life cycle. So we looked at over a 30-year period how much each option would cost to operate. So you've got your bar graph. The grey bar indicates the energy cost, so that's your operational cost over that 30-year period. You've got the yellow section is your maintenance costs over that 30-year period, and blue is the replacement cost of plant, and the orange is the initial capital cost. So immediately you'll see that the electric boiler option is the cheapest in terms of capital cost, and the cheapest in terms of maintenance costs. However, the actual energy cost to operate is very, very high, and that makes it the most expensive over that 30-year period. So that one was discounted for that reason. It was just too expensive to operate and not economically viable for the council to actually to service over that 30-year period in terms of their electrical bills. The air source heat pump was number 3 in terms of performance. You had you had a relatively high capital cost, but you do have to replace the technology over that 30-year period. So typically air source heat pumps might only last 15 to 20 years before the actual heat pump needs replaced. Therefore, we have to account for that replacement. There's also maintenance costs. However, when you compare the operational running costs with electric boilers, is significantly less. So it goes from electric boilers at 43 million compared to 29 million for the air source heat pumps. And then number 2 in the performance was the water source heat pump. So that's taking energy from the Clyde and upgrading that energy to useful heat, which is then circulated to each of the buildings associated with the network. And that had slightly higher capital costs because ultimately water source heat pumps are generally more expensive than air source when you account for the water connection to the river. Slightly less replacement costs, very similar maintenance costs, but the operational running costs go down quite significantly. So it goes from 29 million to 17 million. So that's quite a big reduction. And then number 1 in terms of performance was the 5th generation heat pump. So that's your low grade heat circulating to each building, then locally upgraded at each building. So that was number 1 in terms of performance. And that's largely because the energy cost, that operational running cost, that grey bar goes from 17 to 13. So you're taking advantage of that increased efficiency of that 5th generation technology. The purposes of the feasibility study, we did look at potential locations of energy centres and the proposed kind of heat network route. And I think this diagram just kind of helps summarise how close the buildings are together and how potentially you could create a viable heat network. And that would essentially quite significantly reduce the council's carbon footprint from day 1 of its operation. I should also add that all the 7 buildings that we included in the study are all served from the gas network at the moment. So they're all served by gas boilers. So by switching to electricity, particularly in Scotland, where our grid is incredibly green and the carbon factor of electricity is significantly less than gas, the council would immediately receive that carbon credit from day 1 of the system's operation. And with all options that we proposed, again, because we're not taking a fabric first approach, all buildings could connect to the district heating network from day 1 without pressure on the fabric to perform better. Now, that was the presentation with regards to the district strategy and how that can complement the waterfront. But when we look at the waterfront in isolation, and some of the figures that I've presented earlier in the presentation, the building, the existing building itself, is obviously a high energy consumer. The building has some quite extreme temperature profiles throughout its footprint. So Alistair talked about the relationship between the ice rink and the swimming pool. And I think that's incredibly important because essentially we have an ice rink where we're conditioning air at 12 degrees in order to maintain the ice on the floor. But then some of the adjacent spaces are heated to 31 degrees where we've got swimming pools and leisure pools. So you've got a building which is predominantly heated and cooled via air, via big air handling units. And you're having to condition spaces at quite extreme temperatures, from 12 degrees to 31 degrees. So that explains why the building has such a high energy load. The building itself was constructed in the late 1990s. So it's probably 25 years old, roughly. And what we felt was that the majority of plant in the building hasn't really been upgraded in that 25-year period. So any plant that has been replaced is generally reactive maintenance. So if the boiler had gone offline. They've replaced the boiler, but there wasn't too much kind of planned preventative maintenance associated with the plant replacement and upgrade. So, there was opportunities where, we could, make improvements to the building services to help improve the building's energy performance and carbon footprint. So, looking at the ventilation plant, the heating plant, the cooling plant, they're all generally technology which was installed 20-25 years ago, and have performance limitations associated with that type of technology. So we developed a proposal to help decarbonise the building, looking at the various services that had the energy consuming attributes. So just to briefly talk about the various proposals that we presented in our report. Domestic hot water, with the high number of changing facilities and showers, there is a lot of stored water in the building, and there's a lot of distribution pipework in the building. The domestic hot water vessels and the pipework haven't really been upgraded since the building's original construction, and a lot of the insulation was generally of poor quality. So we felt that immediately you could enhance the insulation on the pipework, you could enhance the storage vessels insulation levels, and you could also look at reducing the amount of hot water storage in order to reduce storage loss associated with the hot water distribution system. And although we recognise that, we do need to store hot water for a leisure centre where you've got lots of showers and lots of domestic hot water requirements, but there is areas in the building where you could potentially take advantage of point of use electric water heating. And for example, staff rooms, tea prep rooms, toilets that are away from the main changing village, they could essentially just have local hot water generation, and that would take quite a large amount of hot water distribution pipework off the system. And we by default benefit from the energy savings associated with that reduced distribution loss. The heating system at the moment, it is gas boilers. There is also a CHP which was installed about 12-15 years ago, but it's predominantly a gas boiler heating system. So obviously utilising fossil fuels, and with the introduction of a district heating network, which is served by a water source heat pump or a wastewater heat pump, that's an immediate opportunity to decarbonise the heating system. And if, for example, the client didn't want to go down the route of district heating, you could equally have a local system serving the waterfront leisure centre. So ultimately, the building is, by its name, adjacent to the river. So you could have a local water source heat pump connected to the leisure centre only, and have a low carbon heat source serving the building. And that's also equally true with ground source, because of the large car park and adjacent areas which were undeveloped. There's opportunities there to create a borehole array. So very briefly, if we did have ground source heat pumps, we felt without any significant without any significant fabric upgrade, we would probably need about 70 boreholes, and each borehole would have to be 7 metre spaced and go down around 180 metres based on the geographical conditions of the ground at Inverclyde. Now, cooling. This building has a large cooling load, and it's got a cooling load for two reasons. You've got a cooling load associated with ice generation for the ice rink floor, and then you've got another cooling load associated with the ambient air of the ice rink itself. So there's two big chillers currently serving the building, and there's opportunities there to cool more efficiently. And one of the immediate things we thought was, at the moment, the cooling is water to air chillers. So all the heat rejection just goes straight to atmosphere. And what we felt was this building is a building that has a quite a significant cooling load throughout the year, and also quite a significant heating load throughout the year. So, there's an opportunity there for heat to be transferred from the chiller to the heating circuit, whilst at the moment it's just getting rejected to atmosphere. So our proposal would be, rather than water to air chillers, we go water to water. And essentially all the rejection from the chiller plant goes to the swimming pool heating system. And that's a very easy win, and provides a decarbonised heat source for the swimming pool, which could significantly reduce the reliance on the gas boilers. That argument was further amplified by the fact that the chillers at the leisure centre have now surpassed their economic life. So the council were looking to change the chillers, and with that change in specification, and by introducing that link between the chiller plant and the heating plant, there was a great opportunity there to transfer that heat and take advantage of that kind of lower carbon heat source. And for ventilation, the building has 8 or 9 large air handling units. They're all original. They're all installed in the late 1990s. So the Pacific fan powers and the heat recovery are all of that generation in the late 1990s. So again, there's opportunities there to refurbish the air handling units, upgrade the internal components, and provide better heat recovery, more efficient fans, and essentially provide that conditioned air more efficiently. Lighting, again, there's obvious benefits of upgrading the lighting to LED and providing sensors on that light to daylight. The building has lots of glazing, so there's opportunities there to link the lighting to the daylight levels. And also, because we have specialist pool plant, again, they're all 25 years old. So with modern advances in pool technology, we could upgrade the filters to ceramic membrane filtration, which would save water by around 50%. We can take advantage of more modern methods of chemical dosing, and upgrade the circulating pumps associated with the pool plant to more efficient pumps. The building also doesn't have any local generation at the moment, so there's no local electrical generation, but there is opportunity. There is a big south-facing elevation, which is currently heavily glazed. So it's maybe as part of a future kind of fabric upgrade, there's opportunities to replace some of that glazing module with photovoltaics. And that could be an opportunity for the building to generate its own electricity. Now, we did this study probably a year ago, Alistair. Yeah. And since then, the council came back to us and said, we appreciate all the work you've done, and this is something that we're certainly going to take account for future kind of development plans, etc. But at the present moment, this building is economically very, very expensive to operate, and we've got a plant that's now beginning to fail. So we need to do things now in order to make the building operational. And one of the issues that they had was the chiller plant was reaching end of life and was beginning to fail and was not particularly reliable. So what we're currently doing is we're looking at replacing the chillers at the leisure centre, which are currently water to air chillers with water to water chillers. So again, immediately taking advantage of the heat rejection of the chillers. And these chillers are used throughout the year. We always need to generate ice, even in the coldest depths of winter. The ice chiller is operating at -12 degrees in order to maintain the ice floor. So the chillers are on all the time, and they're always rejecting heat. So let's get that heat from the chiller and transfer that heat to the swimming pool, which again has a 365-day heating demand, irrespective of the temperature outside. So we're currently developing a design looking at upgrading the chillers to water heat chillers and transferring that heat to the swimming pool. But we need to do that within a live and leisure centre environment. So we can't afford to decommission the leisure centre. It's a big part of the community. It's one of the few ice rinks in the area. Probably, in fact, one of the few ice rinks in the west of Scotland. And I think it's only the second swimming pool in the Inverclyde Council portfolio. So, you know, politically, we need to keep the centre open. So we're looking at, you know, opportunities to create prefabricated modules. So essentially fabricating the plant room for the chiller plant off-site. And that means that when the chillers are brought to site, there's less disruption, there's less building works on site, and a lot of that work's done off-site. So there's massive benefits with the prefabricated route in terms of benefits to program and benefits to the site itself. And we're essentially looking at prefabricated modules and reducing the actual construction time on site from what would conventionally be 6 months down to 2 or 3 months, because a lot of that work's done off-site. So that should help maintain the facility's operational capacity and disruption, but provide the council the opportunity to decarbonise its cooling system and heating system using a more efficient chiller strategy, and kind of do that in a cost-effective way, and also a future-proofed way. So whatever we're doing today, we're also got our eye on any future district heating system or any future fabric strategy. And it's important that that kind of complements any future works to the building. And I think that's everything from myself. So I think we've gone slightly over, so apologies for that, Claire. But it was quite a lot to go through, so hopefully we've still got plenty of time for Q&A.
Absolutely fantastic. Thank you so much, Alistair and Amit. Really insightful and really detailed. So thank you so much for those questions, those details rather. Opening the floor to any questions. If you don't want to unmute yourself, please do use the chat and hopefully have lots of questions. While we're waiting for those to come through, I just have a question about kind of what the next step is in terms of your involvement and with this project.
I think I think this a building of this size and its nature is there's always going to be work happening in the building. So, I mean, going back 2-3 years, we replaced all the emergency lighting and the fire alarm and all the electrical safety systems, which had reached end of life. Now looking at the AC and anything we do, we do with an eye for the future. So, you know, that was one of the drivers behind the chiller replacement. The council could have quite easily adopted a like-for-like approach. So, you know, water to air, and just do what they've been doing for the last 25 years. But you know, encouragingly, they saw the benefits of spending a little bit more now, but getting that advantage over the next 10, 15, 20 years. So I think the project or the building will always generate projects, and that will range from, you know, kind of replacement of existing plant and assets to the more significant kind of fabric improvements and thermal improvements. Alistair, I think that's fair to say.
Yeah, I don't think there's any immediate plans to do anything in terms of, you know, the thermal improvements, but there are issues with the building fabric at the moment. So, you know, the south facade, which had the kind of ribs on it, that there is a curtain walling system on that at the moment, and there is water ingress issues with that. So at some point they're going to have to deal with that. I think I'd mentioned about the involvement of a structural engineer. It may be that they just need to replace it like for like, potentially, you know, because obviously there'll be different loads and things depending on what we do. Even if we change that to maybe triple glazing or something like that, the load profile completely changes then. But even I touched on the thermal bridging issue as well with these sort of ribs on the building. And that's something that I think we would recommend that they look at a little bit sooner rather than later, because there is definite steel corrosion on the inside of the building because of that sort of moisture and condensation issue. And to be honest with you, I think it could be resolved fairly simply as well, as we're kind of shown in the study and the presentation there. So I think that would be our kind of recommendation there, is to deal with anything that's really kind of critical there at the moment, but relatively easily solved. but then probably just focus on the M&E items and moving above that.
Yeah, because the building's quite interesting because it's not essentially an old building. You know, it's only 25 years old, so you know it's still got a lot of life left in its in its structure, in its fabric, in its approach. But you know, with the increase in gas and electric prices, you know, it's further amplified how much this building's cost to operate. And, you know, local authorities, you know, they have large pressures to provide facilities like ice rinks and swimming pools. And but when you look at, I mean, this is why I showed some of the graphs in the presentation. You know, the amount of energy that the waterfront leisure centre is consuming, it's like equivalent to like 10 primary schools. To put it into perspective. And that's not necessarily new build primary schools, that's maybe existing 1980s, 1970s buildings, you know, which aren't particularly energy efficient. So from a council perspective, by making a carbon dent on the leisure centre, you know, that does significantly complement its overall carbon agenda with regards to decarbonising their estate. And there is relatively simple things you can do to do that. And that's why I chose the example of the chiller replacement. You know, so that's not a multi-million-pound project, you know, but it's a project that we feel could potentially, you know, take quite a significant percentage of the building's carbon footprint. And that happens within, you know, 12 months from design to handover. So, you know, these are what we classify as the easy wins. And equally, there's probably things you can do with the fabric, you know, like probably bridging and the airtightness that you could get benefits relatively low cost quite quickly.
Yeah, definitely. It's about that cost benefit analysis. And to stray slightly off a topic, we've done other studies for universities, looked at the Strathclyde University stock, their entire stock, and they've got a district heating network there, so we could quite easily identify where the big energy users were. And I think it's that what Amit's touching on there is really important for local authority clients, is understanding where that energy is getting used and where the big hit items are, you know, because like you say, Amit, you're doing a little bit of work on that on that leisure centre is probably more cost effective than doing a lot of work on a number of primary schools, for example. You know, and a lot less hassle as well when you take into account, you know, the disruption that every project inevitably causes.
Value for money.
Exactly, yeah. So understanding the entire stock in terms of setting up that initial strategy to get to net zero is critical.
Yeah, brilliant. We've had some questions come in on the chat, which is fantastic. So thank you very much. I'm conscious of time, so if we can try and get through as many questions as we can. Yeah, let's have a go. Zach's asked, would an air source heat pump have a better COP during summer usage, which is a larger part of pool heating than other buildings?
Yeah, I mean, so the air source heat pump, the coefficient of performance obviously varies from month to month, and yeah, you're absolutely right. It is more efficient in the summer than it is in the winter. Our approach, we took a seasonal approach in our feasibility study. Inverclyde doesn't particularly benefit from good winters, it's fair to say, and you know, so in the peak of winter, it's quite common for temperatures to go below 0 degrees. So overall, although there was you know, high efficiency attributes in the summer, but overall the air source heat pump SCOP was about 150% less than the water source heat pump and the wastewater heat pump, which were more stable. So water temperature and wastewater temperature doesn't significantly change season to season. So more costly to purchase, more costly to install, but you do gain more efficiency.
Yeah, brilliant.
And
thank you so much.
Arguably also longer economic life as well.
Yeah, multiple factors then to make those decisions. Thank you very much for that one. We've had a question from Steffi. Was there not an option for a wind turbine, giving the very high electric demand all year round and exposed position?
not something we looked at in any great detail. I think the issue we would have with wind turbine is, you know, the electrical loads for the waterfront leisure centre are so high. You've got, you know, you've got 2 chillers which are probably 250 kilowatts each. So that's before you even look at lighting and small power, you're at 0.5 megawatt. To get some of that electricity from wind turbines, you're looking at pretty big turbines, and imagine the planning and the noise and the structural implications of those turbines on the banks of the Clyde are going to be quite a challenge. Alistair.
Yeah,
Okay.
it's right in the town centre. I mean,
Okay.
you know, it's, you know, it's, you know, it might raise a few eyebrows, would imagine. Something like that.
And that links on to Tony's question, actually, about were there any additional challenges caused by the location of the centre on the waterfront, i.e. with the AHU plant?
Yeah, I mean, it's a good question. You know, you are adjacent to the Clyde, and you know, that does have an impact on air handling plant and any plant that's connected to the environment. You know, with regards to the higher levels of salt in the air, etc. So yeah, there's a higher specification needed to avoid corrosion, and that is factored into the costing study. So. One thing we did feel was that the air handling plant, you know, it's all original. The building is predominantly conditioned using air, and you know, replacing the air handling units is going to be a mammoth of a task. They're all mostly inside the building, and you know, access to remove and replace is quite restricted. So I think if we were looking at ventilation upgrades, our initial approach would be trying to refurbish the existing units. So essentially maintain the carcass of the air handling unit, but replace everything inside with more modern, efficient components. But yeah, absolutely taking full cognizance of the fact that the building is beside the Clyde.
Brilliant, thank you. Steffi has asked, is there a way to internally transfer the heat from the overheated side to the cold side?
So the heat transfer that we're proposing is from the cold side to the warm side. So we're taking heat that's not needed by the cooling equipment that's serving the ice rink and transferring that heat to the warm part of the building that always needs heat.
Yeah.
Yeah. So that we felt was the most kind of obvious way of transferring energy between parts of the building. And, you know, it makes great sense because you've got an ice rink and you've got a swimming pool all in the same building and all requiring different types of energy per year.
Yeah.
Maybe the question may actually, I'm thinking, relate to the front to the back of the building as well. So we may have an overheating issue at the front of the building where we've got a lot of solar gain. So yeah, there's definitely, I think, scope. You know, we can move that heat or cool around the building, you know, as is required. It's the same strategy essentially.
Yeah.
You know,
we've got a north-facing swimming pool, and that was, to be fair, probably done because of the views. So when you're in the pool, you can see the Clyde. Yeah, nice. So it is a nice view, but from an energy conservation perspective, having large glazing in a pool facing north isn't great practice. But equally, there might be some resistance from the client if we decided to significantly change that.
Yeah. So it was something that we didn't look at, to be honest with you, as part of the fabric, because we did slightly. So it has kind of full height windows. Maybe I can jump back a little bit and just show you. It does have full height windows, and when we were in there, it's clearly been designed for you know, for the view, and it is nice. But there are so the top sections, what we looked at was actually clad in the top sections, replacing the glazing at the top, where there wasn't really any benefit in terms of looking at, you know, visual connection to the outside, just to try and cut that proportion of glass down a little bit. You know, down from 100% down to maybe 70 or 60 or something like that, because it would all impact, you know, the higher values and whatnot. But no, we couldn't strip it all out because it's a fundamental aspect of the building, I think.
Yeah. Brilliant, thank you. Very conscious of time. We've got a couple more questions, so hopefully we can squeeze them in. If Inverclyde wants all its buildings to be net zero by 2030 or thereabouts, how will this happen?
Yeah, I get it. I don't know. Are there a lot of councils on I need to be careful what I'm saying. I do kind of think quite often people at the head of organisations have a habit of saying that kind of thing without really fully understanding what the challenges are, you know, and yeah, there's 2030, I don't know what you think.
I mean, to be fair, that's the Scottish Government target as opposed to a local individual target.
It's but I mean, you could do it just by like Amit says in Scotland, we could simply just transition to electric, you know, and we would pretty much be there by 2030. But the energy that would be required to be generated by not reducing the demand in these buildings through fabric measures would be phenomenal. I think 2030 is a massive challenge. I think 2040 is a massive challenge. I think 2050 is as well.
Yeah.
But I do also kind of think that we are in such a place on the planet at the moment that you've got to aim high. And if you don't quite make it, then people shouldn't be crucified for that, you know, because we've got to try. If we just keep moving these things back, then it's never going to happen. Yeah. And it's so important that it does. So I'm not going to criticise them overly for targeting 2030 because you've got to try.
Yeah, absolutely indeed. Right, we've got 2 more questions and about 2 minutes. So, was air to air considered for this particular areas? Is one quick question, and then is there scope for more natural ventilation in this type of building?
So the natural ventilation, the building is 95% mechanically ventilated, and that's largely because of the types of spaces it accommodates. So with the swimming pool, obviously there's a requirement for humidity control and, you know, temperature control, and that's similar with the ice rink. So I don't think natural ventilation is going to play a significant part in any future works to the building. It's not that type of building that natural ventilation would be particularly viable. The other question was it air to air? Is that what you said?
Yes, I think they apologise in case they missed that point in the discussion.
Yeah, we looked at air to water, so air source heat pumps, but from a operational perspective, the water source and the sewage connections heat source was more favourable. We didn't necessarily look at air to air, but I would imagine that would be similar in terms of performance to air to water.
Brilliant. Super. We are almost on our time. Thank you so much to both Alistair and Amit for your time and your insights and answering all of those fabulous questions. Thank you very much to everyone who's joined us today for joining in with lots of questions and kind of coming along today to listen. Massive thank you very much as well to Abby, who has just put up our poll. If you do have time, please do utilise the poll to vote on how you found this session today. Please do visit the website as well, so the North East and Yorkshire Net Zero Hub, for more information, more details of other sessions, and a massive thank you very much again to our speakers, to Abby, my colleague, and for everyone joining in, and thank you very much. Copies of slides will get issued out shortly, and enjoy the rest of your day. Take care, and it's been an absolute pleasure. Thank you ever so much, everyone.
Thanks very much, Emma. Thank you. Cheers.